Okay, welcome back to our discussion of signal flow graphs. And in this section or video, we're going to talk about actually putting the principles to work by applying them to a cascade, in this case, of a couple of different components, and then reducing it down to a single expression. What we're going to do is we have here and I sort of started out with this drawing of a couple of components, actually three different components. We have a set of a two-port here at the left side with S parameters labeled with an A subscript. And it's cascaded to another two-port over here labeled with a B subscript. And as the last component, it's kind of hanging off the edge here, we've got a one port with a C subscript. Okay, and what we're going to want to do is get the equivalent, let me scroll back, the equivalent expression for the input at the left side by reducing this all down using the techniques we talked about in the previous video. Okay, and it's a little bit too wide to fit on the screen, but that's going to get better. Because what we'll do is, well, we're going to reduce it first of all, and then we're going to be sort of working on the right side and kind of shrinking it down from there and collapsing it into an equivalent, working from the right, collapsing down towards the left. Now, for convenience, I've gone ahead and labeled the nodes with numbers, starting from the right, starting with the number 1, and then below that number 2, 3, 4. I've separated out the two ports, but they're really joined by the same node, so I just repeated the numbers for 3 and node 4. And then at the right end, we have nodes 5 and 6. So that's the output of the B set of S parameters 2-port, and that'll be going into the 1-port C. So these numbers will come in handy when we go through this process of reducing. And we're going to start on the right side. And so what we're going to want to do is combine the C, the 1-port C network together with the 2-port B network. And so let's start taking a closer look at the right side here. And let me make some space to work with. Okay. So one of the things we can notice on the right end is this sort of loop-like structure between the S22B and the S11C branches. And it would be nice to be able to just separate that out into a loop, and then we can apply the rule number 3 from the previous video to absorb that loop into the S21B branch. And it's not entirely obvious just looking at it, but that can be accomplished by breaking apart this number 6 node. And to make that look a little bit more understandable, let's redraw the connections surrounding the number 6 node separately. So if I draw the number 6 node on its own below here, let me write a number 6. And put the node here. If we just look at it, we see that it has S11C coming into it from the right-hand side. And then it's got a S22B coming out and a S12B also coming out. And let me just label these nodes. Okay, so S11C comes from node 5, and S12B goes to node 4, and S22B goes back to that same node 5. So really, these are the same node, but drawing it this way, they've been sort of separated. But now you can see it's kind of just this single node, number 6, with 2 branches coming off of it. We can draw it using rule number 3. We can draw it as 2 separate independent nodes. Let's call it 6 prime, and I'll do like a 6 double prime for the 2 different nodes. But if we look at one of them, what we have is, I'll draw the node, and let me just highlight what I'm looking at initially here. I'm going to look at this section. Okay, so we have a signal coming from node 5 and going to node 4. And we've got S12B and S11C coming in. So S12B coming out and going to node 4, and S11C coming in from node 5. Okay? And then for the other part of the split, I'll highlight that one in a different color. We'll look at this section. So in that case, we've got S11C coming in, and then it goes via S22B, comes in from 5, and goes right back out to 5. All right, so we split that node 6 into two different equivalent branches. Okay, so let's redraw our circuit now with these 2 branches with node 6 split apart like that. So I'll put down our old drawing again. Okay, and so we split node 6 over here. So I'm just going to erase these things that are touching node 6 here. And instead of a single node 6, we're going to have a node 6 prime and a node 6 double prime. Okay, so well, node 6 double prime is still showing on the screen, so let's draw that one. We have a branch coming from node 5 into node 6 double prime, so I'll sort of draw that off to the side here, and that is S11C. And then we have the branch exiting and going back to node 5, and that's got a S22B on it. Okay, and then if we look at bring back node 6 prime in here, it's got S12B exiting from node 6 prime going to node 4. Well, that's still there from our original drawing. S12B, right? And we have S11C coming from node 5 into node 6 prime. So let me draw that. That's a S11C. Okay, so let's create some more space for ourselves. And now we can redraw this again. let me bring down our original drawing. A copy, and okay, so we're totally modifying this side. And we've got a different situation instead of the old Node 6. We've split that apart successfully. Okay, move it up just a bit. Okay, so if we look at this branch going, the branches going into and out of Node 6 prime, we see that there are two branches going in the same direction, and those can be just combined by multiplying them together. So we can replace that with a single branch that is S12B, S11C. So kind of ta-da, we got rid of those two branches, consolidated them into one branch. And now we have also on the Node 6 prime, we have basically two branches going in the same direction as well, which can be combined. And let me just go ahead and draw it. It's kind of in a loop shape, but let me just actually draw it as a loop. So it's a loop with the combination of S11C, S22B. Okay, so now we have a loop, and we have a rule that allows us to integrate a loop into the branches that are going into the loop. That was rule 3 from our previous video. Let's take a quick look to review at that rule number 3 for a brief moment. So here we are with the rules from the previous video. And if we go down to rule number 3, it shows the loop. And to consolidate a loop like that, we divide the nodes going into the loop by 1 minus the quantity of the loop. And the loop then gets absorbed into the branch that precedes the input branch to the node. Okay, so let's go ahead and get another copy of our diagram, and we'll modify it. Okay, so we're going to take the loop and absorb it into the branch that was going into the loop. So we have S21B divided by the loop, 1 minus the loop quantity, which is S11C, S22B. So now the loop is gone. Okay, now we can see we've got two branches in the same direction that can be combined just by multiplying them together. Okay, so I'm going to redraw this as a single branch. Okay, so multiplying the two together, we get S12B, S11C, and S21B divided by 1 minus S11C, S22B. All right. Now we have two branches that are parallel and in the same direction. And with those, we can just add the two quantities together to combine them. So pasting our drawing back down again, I can just fill in the equivalent parameter here that we've calculated graphically. So S11B plus this whole thing. And since I've been having such a hard time drawing today, I'm just going to cut and paste it, or copy paste. So that saves some time. And there you have it. Now we have taken that whole combination of the B 2-port network and combined it with the 1-port C network into a single branch. Okay, so let me center this a little bit. And to continue, we need to do the whole thing over again. You can see we have kind of a 2-port network and a 1-port network tacked on to the output port. So it's kind of the same process, we just have to repeat it over again. So that would make actually a good exercise for you to try yourself. But since it's identical, kind of an identical structure, we're really going to end up with the same results, so to speak, just that instead of combining B and C, we're now combining A and B, so to speak, this appendage 1-port. So you can actually just write down the result for the next combination just by decreasing the subscripts by 1 letter. So looking at this same structure and substituting an A wherever you see a B, and then this entire result wherever you see a C subscript. So let me just say, for temporary purposes, that this whole result, I'll just give it a symbol like theta and use that for substitution. So now what I'm saying is I can write the result for the entire equivalent circuit kind of by inspection, by just mimicking this previous result and substituting in the next subscripts, like I said, 1 subscript lower alphabetically. So let's just do this. So instead of S11B, I'll write down S11A. And then we've got a plus S12, okay, A instead of B. And then I've got a C subscript, so I'm going to substitute the entire expression in, which I've called theta. And then S21 instead of B, I'm going to write an A. And underneath in the denominator, I've got 1 minus theta again, S22A. And that's going to give me my entire result. Okay, so let me just copy this whole thing so I don't have to write it every time. Okay, so I've got that entire expression on the clipboard, so to speak. And let me now draw the entire expression. So it is, anytime I see a theta, I'm going to substitute that whole large expression in. So I have S11A plus S12A, S21A, and then that entire expression. And then denominator. I've got 1 minus S22A, and then that entire expression again. Okay. And so now that is the expression for the equivalent input S parameter for that whole cascaded, two ports cascaded along with a one port on the end. So I ask you, can you imagine trying to come up with that equivalent purely algebraically? That would be quite the algebraic gymnastics. But using the graphical techniques, you can kind of keep some order to it, as much as you can call that order. Now, these techniques have been employed historically to come up with formulas for working with CAD programs. So deriving the formulas for combining S parameter, two ports in cascade, as we have done here, but also more complicated arrangements. And in a day-to-day usage, you might, if you work a lot with test fixtures in measurements, you can use these techniques to come up with an equivalent expression for the various components in your test setup to try to de-embed them. If you're using a test fixture, for example, and some other components ahead of your device under test, you can combine all of those S parameters together for the purpose of subtracting them out of the measurement at the end. Could be another application. But in any case, it's a difficult subject to follow in trying to just read it in a textbook. So I hope the video helped to explain that in a little bit more step-by-step fashion that's a little bit easier to follow. Took me a very long time to figure this all out. Primarily the topic discussed in the first video helped to separate things out as far as what they were considering a node and a branch and so forth. Well, I hope you enjoyed the video, and please like and subscribe, and we hope to provide you with some more insights into working with RF and S parameters and so forth. Thanks a lot.